on uniform circular motion. Remember, uniform is referring to the velocity inside of our system, how the velocity is not changing, but because there is a change in direction, there is still technically an acceleration. A little bit of review. We have our magic circle number 1, which is our horizontal circle. And because it's a horizontal circle, remember the force of gravity will not come into play whenever calculating the centripetal force. We have our two equations. Velocity is equal to 2 pi radius over period squared, and our acceleration is equal to velocity squared over radius, or 4 pi radius times 4 pi squared times radius over period squared. We have our second magic circle, which is our vertical circle, the one that looks like a Ferris wheel. Remember, because this is the vertical circle, the force of gravity will come into effect whenever calculating the final centripetal force for the top and the bottom of our circle, where force of gravity is being added to our centripetal force at the top of the circle to find our final centripetal force, and is being subtracted at the bottom of the circle to find our final centripetal force. So let's do some problems. Justin is driving his 1,500 kilogram Camaro through a horizontal curve on a level roadway at a speed of 23 meters per second. The turning radius of the curve is 65 meters. Determine the minimum value of the coefficient of friction, which would be required to keep Justin's car on the curve. Now, because we're not swinging Justin's Camaro on a string, or we're not going around the moon in his Camaro, we are using the frictional force as our force is centripetal. And again, that's what we have here. If frictional force is equal to our centripetal force. Now, if you remember from way back when, our frictional force is equal to mu times the normal force. And if you break that up even more, you can have our frictional force equal to mu times mass times gravity. Remember, our centripetal force is equal to mass times acceleration. And because there's mass on both sides of the equation, we can get rid of that. We end up with mu times gravity is equal to acceleration. Rearrange that so we're solving for mu. We can use our variables that we have inside our equation to find that acceleration. Divide that by 9.81, and we have a mu of 0.83. Remember, mu does not have any units, so we're good there. We have problem 2. Billy Babjoe swings a coconut on a string in a vertical circle. The string Billy Bob uses is 3 meters long, and it takes about 3 seconds for the coconut to go around the circle once. If Billy Babjoe magically knows that the total centripetal force at the lowest point of the circle is 1 kilogram meters per second, what is the mass of the coconut? Usually we're given the mass and we're trying to find out what the centripetal force is, but here we're actually given the centripetal force and we're going to have to go hunt down the mass. So let's look at here. Remember, the centripetal force at the very bottom of a vertical circle is the original centripetal force minus the force of gravity. So we can split that original centripetal force and gravity up into mass times acceleration minus mass of gravity, which is equal to our centripetal force, which we know is 1. Because we have mass multiplied by acceleration and mass multiplied by gravity, we can factor out that m, and we end up having mass times acceleration minus gravity. We can find our acceleration by using the variables into the equation. We find an acceleration of 13.16. And if we were being asked for the acceleration, remember, we'd only put down 13 meters per second because of sig digs, but because we're still calculating with that number, we're going to keep that number intact, put that back into the equation, subtract that out, divide our centripetal force by our new acceleration, and we have our mass of the coconut, which would be 0.29 kilograms. Again, sig digs. We have our problem 3. During the spin cycle of a washing machine, the clothes stick to the outer wall of the barrel as it spins at a rate of 1,800 revolutions per minute. This radius of the barrel is 26 centimeters. Determine the speed of the clothes which are located on the outer wall of the spin barrel, and determine the acceleration of the clothes. Remember, we need to turn that revolutions per minute into a period, so we're able to use that in the equation. We need to remember to turn that centimeters into meters to be able to use that 26 within our equation. So we have that here. We're going to find our velocity, which is 2 times pi times radius over period. We take in our radius, of course, and it is 0.26 meters per second. No, we have 0.26 meters, what I'm talking about. And over the period, which is 1 over 30, whenever you calculated that revolutions per minute into period. we end up with a velocity of 49 meters per second. And because we've already figured out the velocity of this system, we can just use the easier of the two acceleration equations, stick that 49 in as our velocity, find our acceleration out as 9,200 meters per second. Remember, sig digs. And problem 4. In the display window of a toy store in the local mall, a battery-powered plane is suspended from a string, flying in a horizontal circle. The 631-gram plane makes a complete circle every 2.15 seconds. The radius of the circle is 0.950 meters. Determine the velocity of, acceleration of, and net force acting upon the plane. So first we're going to find our velocity, which is 2 pi radius over period, and we'll end up calculating that out as 2.77 meters per second. Remember, sig digs, sig digs, sig digs. Again, we've already figured out the velocity of the system. We can use the easier of the two acceleration equations. Plug that 2.77 meters per second into our acceleration equation, find an acceleration of 8.11 meters per second. Because this is a horizontal circle, the force of gravity is not going to come into effect whenever calculating the net force, and net force is just going to be equal to our centripetal force. Remember, centripetal force is just mass times acceleration, so we can take our mass of a plane, which is 0.631 kilograms. Remember, we had to convert that from grams into kilograms. And our acceleration equation is just 8.11, and we end up with a net force of 5.12 meters per second, kilogram meters per second. I hope you were able to figure out something in this video, and good luck on your quiz. Have fun.